Modern warfare is no longer just about firepower. It's about survival in environments that don't negotiate. Arctic cold that kills batteries in minutes. Ocean depths where pressure crushes steel like a soda can. Skies so crowded with cheap drones that billion-dollar jets are suddenly vulnerable. Most military machines were designed for battle. These were designed for execution zones, places where physics itself becomes the enemy. There are 4 modern failure zones: drone overload, stealth detection, deep sea pressure, Arctic frost, and only a handful of systems were engineered specifically to survive them. The stakes and the global gamble. This isn't fiction. Nations spend billions as battlefields expand into the Arctic, deep sea, and skies crowded with drones. Failures here collapse logistics, halt reconnaissance, and freeze supply chains. We're counting down 10 machines built for these deadly zones. Stay for number 1, the lifeline of extreme ground operations. Number 10, directed energy weapons. In the drone overload zone, the math is brutal. Firing a $2 million missile at a $500 drone isn't strategy. It's bankruptcy. Directed energy weapons flip that equation. Systems like laser platforms tested by the U.S. Navy can fire concentrated beams at the speed of light for mere dollars per shot. There's no recoil, no ammunition stockpile, just power and precision. But there's a weakness. Rain, fog, dust, and atmospheric distortion scatter laser energy. In perfect weather, it's surgical dominance. In storms, it's dramatically reduced. Directed energy isn't a universal solution. It's a precision scalpel in a chaotic sky. Number 9, electronic warfare jammers. If you can't shoot the drone, shut off its brain. Electronic warfare systems overwhelm enemy signals, severing the connection between pilot and machine. When GPS and command links disappear, drones crash, freeze, or drift uselessly. Modern systems deployed by forces like the Russian Armed Forces and NATO units demonstrate how signal dominance can neutralize entire swarms without firing a single round. The battlefield is now a spectrum war, but it's a duel. Encrypted systems, frequency hopping, and autonomous AI navigation are evolving fast. Jamming works until the drone no longer needs a signal. In the electromagnetic arena, silence can be as powerful as missiles. Number 8, radar-absorbing materials, RAM. Stealth isn't invisibility. It's about shrinking your digital footprint until you look insignificant. Radar-absorbing materials, used on aircraft like the F-35 Lightning II, soak up radar waves instead of reflecting them back. Instead of a bright return signal, enemy screens see distortion, clutter, uncertainty. This delay can mean survival. Because in air combat, seconds decide outcomes. But RAM coatings require meticulous maintenance. Scratches, wear, and environmental stress degrade performance. Stealth aircraft are engineering masterpieces, but they demand obsessive care. RAM doesn't make you invisible. It buys you time, and in war, time is everything. Number 7, infrared signature, suppression. Heat-seeking missiles don't care what your aircraft looks like. They follow fire. Engines burn thousands of degrees hot. A glowing beacon in the sky. Infrared suppression systems mix cold air with exhaust, diffusing the heat plume. Aircraft like the B-2 Spirit integrate exhaust management to reduce thermal signature from below. It's physics manipulation. Reduce contrast, break missile lock. But nothing removes heat completely. At close range, advanced seekers can still detect minimal differences. Infrared suppression doesn't eliminate vulnerability, it narrows it. And sometimes, narrowing the window is enough to survive. Number 6, anechoic coatings. Underwater, sight disappears. Sound becomes everything. Submarines rely on stealth measured in decibels. Anechoic coatings, rubber-like tiles covering hulls, absorb and scatter sonar pings. Instead of bouncing cleanly back, sound waves fragment into acoustic noise. Submarines, such as Russia's Borai-class submarine, use advanced hull treatments to reduce sonar visibility. It turns a massive steel vessel into a ghostly echo. But silence requires more than tiles. Internal machinery must also be isolated and dampened. One vibration can betray position. In the deep sea, survival depends on not being heard. Number 5. Autonomous underwater gliders. Propellers are loud, they consume power, they limit endurance. Autonomous underwater gliders move differently. By adjusting buoyancy and wing angles, they surf through water in slow arcs. No engine roar, minimal energy use. Organizations like the U.S. Navy deploy gliders for months-long reconnaissance missions. They gather oceanographic data, track submarines, and map thermal layers silently. They are not fast. They are not armed. They are patient. In the deep-sea failure zone, endurance beats aggression, and these machines redefine persistence. Number 4. Saturation diving systems. At extreme depths, humans cannot simply dive and resurface daily. Rapid decompression causes fatal damage. Saturation diving systems keep divers under constant pressure inside sealed chambers for weeks. They travel to work sites in pressurized bells and decompress only once, at mission's end. Used in naval and offshore operations worldwide, including support missions coordinated with agencies like the U.S. Navy, this technology enables heavy engineering hundreds of meters below sea level. Number 3. Extreme cold engine systems. At -40 degrees Celsius, metal contracts. Fuel thickens, lubricants solidify, engines seize. Without cold start systems, advanced armored vehicles become frozen monuments. Arctic-adapted platforms, such as variants of the Leopard 2, use engine preheaters, insulated fuel systems, and specialized lubricants to survive brutal winters. Cold start engineering ensures machines wake up when the temperature tries to kill them. Number 2. Extreme cold battery packs. Batteries suffer silently in the cold. Standard lithium systems can lose over half their capacity in Arctic frost. Cold-optimized battery packs use thermal insulation, internal heaters, and chemical tuning to maintain output. Because when power dies, everything dies. No communication, no targeting, no mobility. In the Arctic failure zone, electricity is survival. Number 1. Arctic articulated carriers. When roads disappear and terrain becomes fractured ice, conventional vehicles fail. Wheels sink, tracks struggle. Vehicles like the BVS-10 are engineered specifically for Arctic mobility. They distribute weight evenly and maintain traction where tanks would bog down. In sub-zero logistics corridors, these carriers move fuel, troops, and supplies. This is engineering built not for battle, but for survival. Modern warfare is no longer defined by who has the biggest weapon. It's defined by who can survive the harshest physics. Drone swarms, signal wars, crushing ocean pressure, freezing Arctic voids. These 10 machines weren't designed for comfort. They were engineered for the graveyard, the environments where ordinary systems fail. If you had to operate in one of these failure zones, which would it be? The deep sea? The Arctic? The drone sky? Comment below. And if you want more breakdowns of next-gen military tech shaping the future battlefield, make sure to like, subscribe, and turn on notifications. Because the next war won't just test strategy, it will test survival itself.